Ansys, good afternoon, madam.
Afternoon, sorry.
Ansys, you can start now.
Okay, thank you, sir. Good afternoon, ma'am.
Afternoon.
So here we have gathered to attend the tutorial session. So first, let me introduce Professor Rukmi Datta. He's working as an associate professor in University of New South Wales, Australia. He's also a senior member of ICC since 2015, and he is working in diverse research areas, which have which is through which he is able to publish significant number of articles and books as well. Along with her, we have Dr. Silchar, who is a postdoctoral research associate in the University of New South Wales, Australia. And his research interests include the design and analysis of permanent magnet machines, high-speed motor drives, and the modeling and optimization of the parameters. So I would like to hand over the session to Dr. Silchar and request him to start.
Okay, hi, hello, everyone. Thanks for coming to this tutorial. Okay, so we have met each other. I'll skip the introduction. Let's just go to the tutorial. I'll start sharing my screen. Share screen. Oh, sorry, Professor Sakia, you need to set me. Okay, now I'm the host. Now I can share my screen. Okay, so this is the second day of our, not the third day, but our second tutorial. Okay, so in today's tutorial, we'll refresh the knowledge you obtained from today's lecture. Okay, so basically I'll go through those analytical tools and models you learned from today's lecture, that is about how to estimate the dimension and performance of a motor at the initial stage. Okay, so we will first go through all of these models and do a quick case study, and then we'll go to the most interesting session of today's tutorial. We'll have a Fve workshop, so I will demonstrate how to use Ansys to design a Prius motor, and we'll solve its magnetostatic performance. Okay, so this is the content of today's tutorial. So hopefully by completing today's tutorial, we can refresh the knowledge obtained from today's lecture, and you can learn how to estimate the preliminary size of a PMSM, and also acquire basic knowledge and skills of how to use FEM software and how to build, solve, and analyze a Fe-based magnetostatic PMSM model. Okay. During the tutorial, if you have any question, just feel free to interrupt me and ask me. Okay, so you can type it or just say it to me. Okay, let me turn on the chat window so I can see if you have questions. Okay, from yesterday's, if you still remember from yesterday's tutorial, I talked about the FEA and optimization-based machine design, right? So I said, okay, so even we have the help of FEA software, but still it is very important to use the analytical models at the initial stage, okay? So we can use all of those analytical models and tools and equations to predict the feasibility of this design, like whether this design is practical or not. So sometimes we may get the request, okay, can you design a motor with this power and that speed. So just quickly go through the analytical models so we can give a very quick answer. Okay, that's doable or not. And also it can help us to determine some initial parameters, the size and dimension of the motor, which can help to reduce the computational time of the optimization. It can also help us to determine the constraints of the optimization. Okay, so it is very important to learn how to use these analytical models. I guess the next question is, what can we get exactly? Okay, what can we get from the preliminary analytical calculations? Okay, so like when we first get a request to design the motor, normally we'll get the design specifications and expectations from our customer or industry partner. Okay, so they'll say, I want a motor with what is the rated power, what is the rated speed, base speed, maximum speed, efficiency, power factor, what is the DC bus voltage I can provide to the motor. Okay, so these are the normal specifications we can get at the beginning of a project. And sometimes we'll have more constraints. So sometimes it can be very fuzzy. I want this machine to have very good performance. So they would ask you to design a machine with a certain constant power speed range, a certain air gap flux density, a very low torque ripple. Okay. Sometimes they also constrain the current density and power density. Okay. So at this time, so at the beginning of the project, the first thing we do is to use all of these preliminary parameters or initial parameters in the analytical models and tools we learn from today's lecture and also today's tutorial. Okay, using these analytical tools and models, we can get some preliminary estimations, such as the rated current, the rotor volume, the maximum rotor diameter that is limited by the centrifugal force, and the mechanical stress on the rotor, the maximum stack length, okay, to avoid, shaft resonance. And also we can estimate what is the maximum, the optimum case or worst case power density. Also the air gap distance, the magnet thickness, and so on. Okay. So, and next, what can we do using these parameters? Okay. So we can use these parameters to determine the minimum feasibility of this project. Like what I just introduced, so whether this is a practical thing, whether we can design such a motor or not. And also it can help us to know in advance, so maybe what is the optimum case performance. Although all these analytical models and tools are not very accurate, but if we set the situation to the worst case and the optimum case, so we can get a fairly accurate result, like what we can expect from the design. Okay. And most importantly, it can help us to find the reasonable initial design. Okay. So maybe your initial design can just satisfy all the requirements. Okay. And if the performance of your initial design is very close to the expectation, the design expectations, then it will save a lot of your time and work, to optimize to meet the expectation, to meet the requirements. Okay. Now, from today's lecture, we learned many different analytical tools and models, but because due to the time limit of this tutorial, I will only go through a few important ones with you in this tutorial. Okay, so that is the general sizing equation, the mechanical loadability of a machine, the electrical and the magnetic loadability, and the air gap estimation. And among all the analytical tools, the general sizing equation is the most important one. Okay, so you have learned all of this from today's lecture. This is the general sizing equation. Okay, and actually now the most widely used general sizing equation is proposed by Dr. Huang when he was working with a very famous professor, Thomas A. Lippo, okay? And this equation is proposed in this paper, okay? This paper is published in 1998, okay? But it's still widely used. Okay, so this is the equation. The torque equals to the efficiency times square root 2 pi divided by 4. This is the power factor, winding factor, the linear current density, air gap flux density, diameter of the air gap, and the length of the stack, length of the rotor stack, length of stator stack. They are normally the same. Okay. And also, okay, so we can further simplify this equation to this one. Okay, so this indicates, reveals the relationship between the output torque of a motor and its rotor volume. Okay, how can we get this equation from this? Because we have the diameter square times the length of the rotor. Okay, diameter square times pi divided by 4 will be the cross-sectional area of a rotor, right? So if we have, this is our rotor cylinder. If we know the diameter D and the length L, we know its volume is 4 pi D square times L, right? So we can get from this, go from this to here, get the rotor volume, okay? And also, if in our case, at the beginning of a project, it is easier to know what is the rated torque, but we want to estimate the rotor volume. So we can write this equation, sorry, not this equation, in another form. That is, the rotor volume equals to the output torque divided by 2 times the efficiency times power factor times winding factor times linear current density and air gap flux density. Okay. So sometimes you don't know these 3 numbers. Okay. You can, then in this case, you can approximately treat all these 3 as 1. Okay, that is the optimum case. That means your motor has 100% efficiency, unit power factor, and unit winding factor. So you can simplify this to this, okay? If you don't know these 3 values. And this is very easy to memorize, right? So later in the case study, we'll practice how to use this equation to estimate the volume of a rotor, okay? And the linear current density and the air gap flux density you can find from these 2 tables. Okay, these are values that based on previous studies and engineering experience. Okay, so that means, for example, if we have a silent pole synchronous machine, typically the air gap flux density should be between 0.85 and 1.05, okay? But please note that this is a peak value, okay? This is a peak value. And also we have the typical linear current density for different type of motors with different cooling or different, motor type. These are quite good numbers and very handy to use in conventional designs, okay? But now very often you can see machines with parameters far beyond these numbers, okay? And we'll talk about this later, okay? So this is the generalizing equation and the simplified version. Complex version is just this times efficiency, power factor, and winding factor. It's easy to remember, right? Okay, let's move on. So we have talked about the general sizing equation, which is the most important one. Next is the most critical one, okay? That is the mechanical loadability of an electric machine. We know when a rotor rotates at a certain speed, there will be a centrifugal force, okay? When they rotate, there will be a centrifugal force acting on the rotor, okay? Right? So this is the equation, this very simple and basic equation to calculate the centrifugal force. This is the weight of a cylinder. This is the angular speed, radian per second. And this is the radius, okay? Sometimes it is more accurate to use the centroid radius, okay? Not just if this is the rotor, this is our radius, but the centroid radius is probably between the outer radius and the inner radius of the cylinder, okay? And that is if we divide this cylinder to a quarter, and the centroid radius is from the point of the mass center to the center of the cylinder, okay? So centroid radius is basically the distance from the mass center to the geometric center, okay? But this is just a simplified explanation of centroid radius. If you're interested in this, you can go to read more textbook and papers about introducing about this, okay? And why we say the mechanical loadability is the most critical design consideration, okay? That is because if you don't consider it carefully, there may be a plastic deformation during a high-speed rotation, okay? And when this type of plastic deformation happens, that means your rotor will deform. Originally, it is a perfect circle, and you have a very thin air gap, remember? Okay, so when the plastic deformation happens, so the rotor may deform like this, and the deformed part may touch the stator inner surface and cause this kind of damage, okay? So this is kind of a good situation. So normally when plastic deformation happens, you could get a more severe mechanical failure or damage, okay? The other case is we need to consider the mechanical resonance. The mechanical resonance is we know when the shaft or the rotor rotates, it will start vibrate dramatically when it reaches its natural resonant frequency, okay? And the frequency, the shaking or vibrating frequency of the rotor normally increase with its speed and proportional with its speed. So the higher the speed, the easier to reach the resonant frequency, okay? So we have to consider the mechanical stress and the mechanical resonance of a rotor very carefully, okay? Otherwise, our motor may have, very severe mechanical failure, damage, or even catastrophic destruction. So it is very important to consider the mechanical loadability. Okay, how do we evaluate the mechanical loadability of a motor at the very beginning? Okay, that is at the initial stage when we don't know the specific parameters of a motor. Okay, to estimate the mechanical stress, we can use this equation. Okay, that is the hoop stress in a cylinder or a ring equals to C dot times rho. Rho is the mass density of the material times the radius square times the mechanical angular speed in radian per second square, okay? C dot equals to 3 plus V divided by 8 for a smooth homogeneous cylinder. Okay, so this is very clear and straightforward. That means it's just a solid cylinder. And here the V is actually the Poisson's ratio of the material. And what is that? I remember Professor Data introduced about this. So that is when, let's say when we have a cubic thing like this, if we apply a force or stress on its top and bottom surface, okay, the first thing we know for sure, the length will extend, right? But its cross-sectional area will also shrink, right? So the Poisson's ratio is the factor that used to describe when you pull a material, how much it shrinks at the other axis. Okay, so that is the Poisson's ratio of the material. Okay, so for solid cylinder, this is our seat dot. But for a cylinder with a small bowl, seat dot will equal to 3 plus V divided by 4. Okay, which is this case. You have a very small bowl at the center, and this is very close to the situation of a solid rotor with a shaft bowl. Okay, because the shaft is normally relatively small compared to the rotor diameter. The third case is we have a very thin cylinder, which is this case. Okay, so instead of having a small shaft bowl, we have a large hole in the center. So it's a thin cylinder. Okay, and normally we use, for this case, we can use this equation for electric machines with a retaining sleeve. Okay, that is in this situation. This is a SPM-SM machine, surface type, permanent magnet, synchronous machine with sleeve. So these are the magnets. And this black one, this is a sleeve, okay? Normally you will see this type of sleeve for high-speed SPM-SM machines, on high-speed SPM-SM machines, okay? That's because magnets are very fragile, okay? It cannot handle the centrifugal force at high speed. So we need to use a protective sleeve to cover the magnets. And these sleeves are normally made with high strength material, such as Inconel sleeve, carbon fiber, and titanium. Okay. Okay. But one thing you need to notice is, although in most cases, these magnets will be glued to the rotor surface, okay? But we all know the glue is not reliable, okay? So maybe one of the magnet is very solid glued to the rotor, but maybe one of it is not glued well. So in mechanical analysis, at the initial stage, we'll consider all magnets not glued to the rotor, okay? That means the centrifugal force acting on each of the magnet will eventually acting on the sleeve, okay? So the sleeve need to handle the centrifugal force of itself and also the magnet. Okay, but to consider the centrifugal force acting on the magnet in this equation, we need to use an equivalent mass density. Okay, so this is equation to calculate the equivalent mass density. That is the density of the sleeve times the volume of the sleeve plus the density of the magnet times the volume of the magnet. Basically, it's the total weight of magnet and sleeve divided by the volume of the sleeve, okay? So this equivalent density of the sleeve will be much, much larger than the density of the sleeve itself. Okay, so it's similar to have a same ring rotating at the speed omega. Okay, this ring has the same weight of the thickness of the sleeve, but it has a weight that equals to the weight of magnet plus the weight of the sleeve. Okay, so we need to use this equivalent mass density in this equation to estimate the mechanical stress acting on the sleeve. Okay. Okay. The other case is we could have a more complex interior permanent magnet synchronous machine. Okay. So this is a kind of the most basic version IPM-SM machine that is called the flat type. Okay. So, but in this case, you cannot apply this equation anymore because the stress near the iron bridges is normally much, much higher than the stress calculated using this equation. Okay, you need to use other equations, more complex analytical models to calculate stress on that. So you need to calculate a reference stress, and you also need to know a stress concentration factor. You multiply these two values together, you can get the maximum mechanical stress. Okay, this is the field I have been working on in the past 4 years. So if you're interested in this, you're welcome to send me a message or email. We can discuss about this together later. Okay, we have published a few papers about this topic. I will copy the title of paper, paste it on the PPT of tomorrow's tutorial if you want to read them. Okay. Okay, but at this time in this tutorial, we'll only focus on the simple version, simple situation. Okay. Okay, so this is how we estimate the mechanical stress. Next is how to consider the mechanical resonance at the beginning, at the initial stage of a machine design. Okay, so this is equation that can be used to estimate the maximum rotor length for the motor to operate below its first critical speed. Okay, what is the first critical speed? First critical speed is the speed of the rotor that makes the rotor, the shaft, reach its first order resonance. Okay, so you can also have second critical speed, that is reach the second resonance of frequency, a third critical speed. Okay, basically, if your speed increases, okay, so if you have your first critical speed here, normally you have your second, let's say your second critical speed is this. Okay, so your motor can work in this region with no resonant problem, and you can also skip the first critical speed and make your motor operate between the first and second critical speed. Okay, so this is possible. Okay, but you need to accelerate through the first critical speed very fast, and also you may need other protections in the motor or the motor frame to avoid severe vibration happen at this time. But in most cases, we'll try to avoid the machine operate at speed beyond the first critical speed. Okay, so you should use this equation, and n is the order of the critical speed. So if you want the motor to operate below the first critical speed, n should equal to 1. Okay. KSF is the safety factor. That is because this is a very preliminary or very fundamental analytical method. It's not very accurate. So we need to consider relative large safety factor. It should be, normally it should be larger than 1.5, and it can go up to 3 or even 5, depending on the design, okay? This is the mechanical angular speed, which the unit is radian per second. And E is the Young's modulus of the material, okay? For steel, like steel that used for shaft, okay, it's normally 200, normally around 200 gigapar, okay, plus or minus. I is the second moment of inertia of the area, okay? So for a cylinder, I equals to pi times the outer diameter to the power of 4 minus inner diameter to the power of 4 divided by 64, okay, for a cylinder. And here it said DO and DI are the outer and inner diameters. And finally, S is the cross-sectional area of the cylinder. And this is the mass density of the material. Okay, so for motors with a solid rotor, it is okay to directly use this equation with this I, okay, the moment of inertia of a surface, because you have your DO, you have your DI, and it is a solid rotor, meaning this solid rotor can also help to strengthen the robustness of the whole structure. But in another case, when we have laminated rotor, okay, then you can't use this equation. You can't use this equation. That is because laminated rotor is actually a stack of very thin laminations, and they are not glued together. Normally, they are not glued together. So we consider they don't have any axial bonding effect. They don't have any axial bonding force, okay, that can help prevent shaft resonance. So we consider only the shaft is taking all the vibration. So we only consider shaft resonance in this case, but similar to the previous case, we need to develop an equivalent density to consider the weight of the rotor laminations. Okay, so in this case, the density of the shaft should equal to this, okay? It is the density of steel. We assume the lamination and the steel have the same density times the volume of the shaft plus volume of the rotor, okay, divided by the volume of the shaft, okay? And because we are only considering the shaft, and the shaft is a solid steel cylinder, so we only have, this time we only use DI, which is this value. We don't use DO, okay? And also your S changes because now the cross-section area becomes the cross-section area of the shaft, okay? So this is how we consider the mechanical resonance of a machine. So then let's say for project, you're told you need to help me design a motor to provide a certain power, speed, and torque. You can use the general side equation to get the rotor volume. And if your rotor diameter is constant, then you can easily get the length of the rotor, and you put it into this equation, then you will know whether this rotor will operate beyond its critical speed or operate below its critical speed. Okay, so if it's operate below its critical speed, then it's a safe design. Okay, it's doable, and it's normally there won't be a severe problem for us. But if it beyond the critical speed, then you need to consider very carefully, okay, whether this project is doable and how, if the first critical speed is not, we can't avoid it, how do we solve this problem? Okay, it's normally either selecting a much stronger material for the shaft, okay, stiffer and stronger, or we reduce the length of the rotor, or we make the rotor lighter. Okay, there are still ways to avoid operating beyond the first critical speed. Okay, up to here so far, do you have any questions? Any questions about the general sizing equation, the mechanical loadability, especially the maximum length of the rotor? Any question? Nope. Okay. Then let's go to the next slide. Okay, so on this slide, I'll talk about the electrical loadability of electric machine. Okay, so you have learned about this actually from today's lecture by Professor Data, the electrical loadability, and also which is also the current density of a machine, is mainly limited by the copper loss and cooling related factors. But there's no simple solution to accurately evaluate the electrical loadability of a machine at the initial stage, because there are too many factors that can affect the electrical loadability of a machine. Okay, so but people summarized from previous studies and using engineering experience, they summarize the values in this table. So these are the linear current density, typical values, and the current density, okay, a amp per millimeter square. This is kiloamp per meter, okay, for different type of machines with different cooling solutions, okay. So these are the values. These, like what I said, these values are very good and handy to be used in conventional motor designs. But nowadays we have many new materials and technologies that can help us to design electric machines more aggressively. Okay, so now it is very often you can see machines with current density much higher than these values. Okay, they exceed the range and much higher than this, especially in the EV and drone industry. Okay, they have been constantly pushing for higher power density and better performances. So it's kind of normal to see machines running with ratings higher than this. Okay. And this is the magnetic loadability of the machine. Similar to the electrical loadability, it is affected by many factors, and the power, speed dependent iron loss, cooling, and even mechanical stress. Okay, so now we can't accurately estimate exactly what is the magnetic loadability of a machine, but we have in the previous table the suggested air gap flux density. Okay, and also you can use this graph to approximately estimate whether your machine exceeded its loadability or not. Okay, but it is for conventional design only, because many new designs exceeded these constraints. Okay, so for example, it says for synchronized cylindrical rotor machine with a laminated rotor, rotor surface need to be smaller than 130 meters per second. This is, in most cases, it is correct, but many new IPM-SM machines or SPM-SM machines have exceeded this value. Okay, the rotor can reach 200 meters per second or even higher. Okay, next is how we estimate the air gap of a machine. Air gap is also, I know the air gap is very small, it's tiny, it's thin, it seems like something we can neglect, but no, air gap is the most important part of an electric machine. So that's where the magic happens. That's where the torque is generated. Okay, so it is very important to have an analytical method or other method to estimate the air gap or to predict the air gap of a machine. Okay, so normally for induction machine that is supplied by 50 Hertz supply, the air gap can be calculated or estimated using this equation. Okay, this P is the power, and this small letter P is the pole pair. Okay, but in this tutorial, we focus on DC and synchronous machine. Okay, because this is a course about PMSM machine design. Okay, in DC and synchronous machines, the air gap is basically constrained by the permitted armature reaction. Okay, so we have to ensure the armature reaction, which is the flux caused by the current linkage of the armature, and we have to ensure this armature reaction does not reduce the flux density excessively on one side of a magnetic pole. Okay, otherwise the machine won't rotate. And to meet this condition, we have this equation. Okay, this is already simplified. The derivation process is a bit long, so if you're interested in this, you can go to read this book, the textbook, Design of Rotating Electrical Machines. But if you just want to know how to estimate it, this is equation you can use as a handy tool. Okay, so to have a functional synchronous machine, your air gap must be larger than gamma times tau times the linear current density divided by the air gap flux density. Okay, gamma is a coefficient. Okay, and you can find the coefficient gamma from this table. Tau is the pole pitch. Okay, and then AA we get that is armature linear current density. So this is how you estimate the air gap of a synchronous machine. Also, you can use this to check whether a given air gap is used, whether the air gap will work or not. Okay. From today's lecture, like I said, we learned many other analytical models and tools. Okay, like how to calculate the pole pitch factor, how to calculate the distribution factor, and the typical torque per volume value, yoke thickness, pole pitch, phase zone, winding resistance. Okay, but due to the time limit, I can't go through all of them. Okay, and if you haven't worked in the field of electric machine, it's gonna take some time for you to really understand all these analytical models. But I know it's easy to understand the meaning, but it's difficult to know. It takes some time to know when and where you should apply these equations during a machine design. Okay, so yeah, in this tutorial, we'll only go through the most important ones and the most critical ones. Okay, so I have talked enough. Now it's your turn, okay, to try to calculate why the answers all come out. Okay, let me hide them. Hopefully it's still okay. Yes, now it's your turn to try this case study. Sorry for that. Okay, so in this case study, we have a surface type PMSM machine with ink canal sleeve. Okay, the ink canal sleeve. I also hide the drawing. Okay, let me delete this. Just pretend you have never seen the answers. Okay, okay. So we have a SPM SM machine with ink canal sleeve, as shown, and it has the following specifications: the sleeve diameter, the sleeve, which is the outer diameter here, is 60 millimeter. The sleeve thickness, HSLV, the sleeve thickness, which is this, is 1 millimeter. Okay, the magnet height, or you can also see the magnet thickness, is 3 millimeter. The rotor length is 1 meter. I just want to simplify the calculation for you, so it's 1 meter. And the mass density of magnet and ink canal sleeve are 7,500 kilometer per meter cubic meter, and 8,000 kilogram per cubic meter. Okay. Yield stress of the ink canal sleeve is 1 gigapascal. What is the yield stress? Okay, so yield stress of a material is the stress when plastic deformation happens. So you need to make sure when this thing rotates at maximum speed, the mechanical stress does not exceed 1 gigapascal. Okay, so using this equation and consider it as a same cylinder, and this is the equation, like I said, this is the equation to calculate the equivalent density, to consider the centrifugal force acting on the magnet. Using these three, can you estimate the maximum rotor speed? Okay, I'll give you 3 minutes to try this. Okay, so have anyone got the answer? What is the speed you calculated? No? Okay. Okay, so these are the answers, and this is the first time you see these answers. Okay, so at the beginning, we need to calculate the diameter of all these values, the value of all these diameters. And then we need to calculate the volume of the sleeve and the volume of the magnet. To calculate the equivalent density, which is easy, we just put all the numbers into it. We can know and we can get the equivalent density of the sleeve, okay, to be 3 times 10 to the power of 4 kilogram per cubic meter. And this is much higher than the real density because we consider the weight of the magnet, okay? Then put all the values to this equation, and very easily we can get the maximum speed, okay, for this rotor to rotate safely. It's around 6,000 radian per second, and that is approximately 58 kilo RPM, okay? But you can't use this value directly as the maximum speed, okay? So normally what we do is we divide this by 1.5, which is a safety factor. So we can see, okay, roughly it is safe for this machine to rotate up to 38 kilo RPM. Okay, so this is a very high speed machine. And normally you only need these sleeves for high speed machines. Okay, the second case study. So this one is more interesting. I hope you all try to do this. So we are requested to design a 48 slot, 8-pole liquid cooled IPMSM that can deliver a maximum power of 50 kilowatt at a base speed of 1200 RPM for 20 seconds. Okay, so which means this liquid cooled machine can only deliver its maximum power for a short period of time due to cooling reasons. Okay, so that means when it is delivering the maximum power, its current rating is much higher than the conventional value. Okay, so when it operates at maximum power, it requires a very high linear current density that is 200 kiloamp per meter. This design needs to achieve an efficiency of 90%, a power factor of 0.9, okay, at the maximum power operating condition, and also ensure it has a reasonable performance. We selected its air gap flux density to be 0.9 Tesla, okay? So first question, what is the maximum torque of this IPMSM? And second, please estimate the rotor volume of this IPMSM, okay? And then we know that the 48 slot 8-pole machine has a unity winding factor. That means this value is 1. So just calculate the maximum torque, put it into this equation. You have the efficiency, you have the power factor, you have the winding factor, you know A and B. Just calculate the rotor volume. Okay, please do the calculation. Okay, I'll give you another 3 minutes to do the calculation. Okay. Have anyone got the maximum torque? What is the maximum torque value you get from this case study? No? Yes, that's correct. And did you get the rotor volume? You just need to put the torque here. This is 0.9, this is 0.9, this is 1, this is 220 kiloamp. This is 0.9. Divide by square root 2. Okay. So yes, 398 is correct. I just approximated the value to 400 Newton meter. Okay, then we put the maximum torque here, and then like I said, just put all the values here. Okay, the reason we need to divide 0.9 by square root 2 is this is the peak air gap flux density. Okay, so the generalized equation tells us the rotor volume should be approximately 0.0019 cubic meter. I know this sounds very abstract, but what if I tell you this is the real motor? Okay, so these are dimensions and parameters of a real IPM asset motor, and that is a famous machine, a famous machine of the 2004 version Prius, Toyota Prius electric vehicle. Okay, so this electric machine, it is installed in the 2004 Prius. Okay, it has 48 slot, 8 pole. It has a maximum power of 50 kilowatt at the base speed of 1200 RPM. And yes, it can only deliver this power for a short period of time, that is 20 seconds during acceleration. Okay, and the real rotor volume of this motor is approximately 0.0013 cubic meter, very close to the number we get. Okay, so that's why I want to emphasize to you that if you want to work in the field of electric machine, this is a very handy tool, very useful equation. Okay. All right, so last case study. After we finish this one, we'll go to the Fe workshop. Okay, this one, okay, for the same machine design, still the Prius electric machine IPMSM. Okay, our calculation tells us the rotor volume should be 0.0019 cubic meter. Okay, we also know this rotor is assembled using electrical steel laminations. Okay, and its rotor diameter is 160.4 millimeter. Shaft diameter is 110.64 millimeter. It has a maximum rotor speed of 6,000 RPM. So what is the length of the rotor? Okay, this is simple. And assume the shaft and rotor material has the same density of 8,000 kilogram per cubic meter, and the Young's modulus is 200 gigapascal. What is the maximum length of the rotor if we consider a safety factor of 1.5? Okay, so you will need to use these equations in the calculation. Again, I'll give you 3 minutes to try this. Okay, and after that, I'll review the answers and we'll check it together. Oh, let's see, idle time of my Ansys model, which I'm going to demonstrate to you later. Let me save it just in case it closes. Okay, I'll go back. Okay, and if you got the answer for this question, or if you need more time, you can let me know. No? Okay. It's fine. Let's go through the answers together. Okay. First, the length of the rotor. This is easy because we already know the volume. We know the diameter. We can calculate. The rotor length is approximately 94 millimeter. Okay. And next, we need to use this equation to estimate the maximum permitted rotor length, okay, for the rotor to operate under the first critical speed. We need to calculate the shaft volume. We need to calculate the equivalent density, okay, using this equation, right? We only need to calculate, to use this equation, we only need to calculate the volume of the shaft because we already know the volume of the rotor. And the equivalent mass density of the shaft will be 2.5 times 10 to the power 4 kilometer per cubic meter. Okay. Then we need to calculate the maximum speed in radian per second. Substitute all these values into this equation. Okay. This is the critical speed order 1 in this case. I is pi times the diameter to the power 4 divided by 64. Cross-sectional area is pi times d square. Oh, sorry, it should be I square. Okay. And we simplify this equation. This is the value we can get. Okay. So we can get the maximum permitted rotor length is 409.6 millimeter, which is far higher than the real rotor length. So this is a very safe design. And this is the case for many real motors. The real motor length, rotor length, is normally much, much lower than the maximum permitted length, because this is the length to avoid the critical speed, which is the ultimate limit, okay? And make the rotor length much lower than this value can also help to reduce the noise, the vibration, okay? Okay, so enough talking about the series and calculations. Professor Data told me many of you are very interested in using FEA to model electrical machine, okay? So now we'll go to the FE workshop. Are any of you currently using any FE software at the moment? Okay, if you are using any one of these softwares, please type it in the chat window. Please let me know. Anyone? No? Okay. Okay. So on the market, there are commercial FE softwares and open source and free softwares. Okay. the commercial ones, the most commonly used in the electric machine design field are these 5 softwares, and there are maybe others, but I see from research papers and I learned from other research groups, these 5 are the most widely used softwares, commercial softwares, okay? The open source and free software, the most commonly used one is called FEM, okay? It has a very simple and basic interface, but it's open source, so you can integrate it to your own control algorithm, to your own program, okay? So that's also how the other 2 software is developed. So the Octave FEM and the Pelican, they are all based on FEMM, okay? The only difference is Octave FEM use Octave, which is a different version of MATLAB to control FEM, and Pelican use Poisson to control FEM, okay? The other one is the Fe2 Multiphysics Model. So you can actually download this toolbox from MATLAB's website. So, okay, so this is actually a MATLAB toolbox. It's free for academic use. Then after you install this module, you can use MATLAB to run some simple FEA models, okay? The pros and cons of commercial and open source softwares. Well, the most obvious one for commercial software is they are very expensive. They'll charge you a fortune to get a license, okay? And they have many redundant systems, many redundant tools you will never use, and that slows your computer. But the advantage is that you can get very comprehensive and very good technical support. They are normally very reliable. They have very friendly, user-friendly interface, and they have some useful tools because they improve by listening to customers' feedback. They develop new tools. On one hand, it's good to have all these tools, but on the other hand, it slows your system, okay? The open source ones, the most important advantage is it's free and it is flexible because it's open source. You can control it. You can just directly communicate with the program, the source program of the software, okay? So it allows you to do more things, different things, okay? But they don't have a very good interface, and you may have cybersecurity issues, okay? But FEM is very widely used, so this one's, I guess this one's fine, and they have very limited function, okay? You need to learn how to use, you need to spend 10 times time to learn, to master the open source softwares than the commercial ones, okay? At USW, we use the Ansys. There's no particular reason for that. It's just our university has agreement with Ansys. So uni provides us the license of Ansys, okay? So we use Ansys. And also Ansys is the most widely used software, okay? So it is very powerful. At the beginning, it's just one small company, but it starts to purchase other companies in the field. So just a few years ago, it bought Maxwell 2D and 3D from Ansoft, okay? So, and then Ansoft used to be the #1 software, FE software in the machine design field, okay? So now Ansys bought Maxwell, so we are using Ansys. When you use Ansys, if you need to solve an electromagnetic problem, like I said, you need to use Maxwell, either 2D or 3D. Mechanical problem, you use Ansys structure. Thermal, you have the thermal and fluid. And shaft, you use Ansys model, okay? So it is software that covers different physical aspects of including thermal, mechanical, and electromagnetic. And that's what we need, because when you design an electric machine, you should not just consider electromagnetic performance, you should also consider its mechanical and thermal performance. Okay. And the platform to integrate all these modules is Ansys Workbench. Hopefully, we'll have time to talk about this in the last tutorial. Okay, but if we don't have time to talk about this and you are interested in this, you can send me a message or send an email to me. We can discuss about this later. Okay. And if you want to try using Ansys, you can download the free student version from this website. Okay, it gives you free access to Ansys high frequency system, Maxwell, Q3D, and IcePack. IcePack is used to analyze the cooling system. Okay, but because it is for student, it has a mass element limit. So for 2D model, you can only have 2000 triangle mass. Okay, so I guess you have already, I remember you have already learned the concept of mesh in Professor Data's lecture. So actually 2000 triangle mesh is not enough to model an electric machine. Okay, but you can download this and practice how to build a multi-geometric model, how to set the current excitations, and how to do the mesh assignment. It's just you can't solve it. But if you're really interested, you can build a model, send it to me, I'll solve it for you. Okay, I'll send the result back to you. Okay. Now, let's go to the software interface. So this, when you open Ansys electronic desktop, this is the interface. Okay, actually, this is the interface after you create a new Maxwell 2D project. In the following tutorial, I may say these names, okay, that refers to the menu, the main menu, the quick menu, which is this here. You can have quick menu of the desktop, wheel, draw, model, simulation, and result. Okay. This is your project manager. It allows you to set settings for each of these, whether it's model, the boundary, the excitation. So here's where you control the model. And when you select any object of a motor, the property will pop up here. Okay, the value, the unit. Okay, and this part is called the history tree. Okay, because it keeps the history, all your operations. Okay, so we create something, it keeps it here. If you draw something, it keeps it here. Okay, so that's why it's called the history tree. And this is the workspace. This is the window. You get warnings and errors. This is the progress window. Okay. Okay, so in this tutorial, I will show you how to build a model, how to build the motor model of the 2004 Prius V-type IPM-SM. Okay, so this is the electric vehicle. It's actually a hybrid vehicle. You have the motor and the generator section and the engine. Okay, and this is the motor, the IPM-SM motor. The cross section looks like this. Okay, so this is a very famous and well-designed IPM-SM. It's kind of like a case that every machine designer need to study. I'll show you briefly how to design this model. Sorry. I hope the time is still enough for me to finish this session, but if the time is not enough, we'll continue this in tomorrow's tutorial, okay? Okay, these are the key parameters, okay? These are the key parameter, geometric parameters and the specifications of the Prius motor. We have the geometric parameters here, okay? We will use these parameters while we build the Prius motor. This is the design specifications, the slot pole number, winding type, how it's cooled. Okay, we won't simulate the cooling and water jacket in this project because that's a bit too long. The stator rotor lamination material, is this, and this is actually equivalent to another material. We'll talk about that later. The magnet grade is neodymium magnet N36. Okay, the maximum voltage in use is 500 volt, base speed 1200 RPM, maximum speed 6000 RPM. Maximum torque at base speed is 400 Newton meter, and it can only last for 20 seconds. Okay. Okay, now let's go to the interface of Ansys. Okay. Okay. So let me start with a new project. So if we start with a new project, it's empty. Okay, there's nothing there. So the first thing you need to do is to create a Maxwell 2D model. Okay, because in this case, in the tutorial, we only do the 2D design, and 3D is actually very similar to 3D. 3D is very similar to 2D. It's just we add a depth to the model. So just go to here, Maxwell, click Maxwell 2D. You can also do this by click on the menu and go to Maxwell 2D design. Insert Maxwell 2D design, and you can get it here. Okay. Okay. So after you set this, there are a few settings I recommend you to do at the beginning. Okay. These are some tips, I guess. So when you do these settings, it's normally easier for you to build the model. So you go to Tools, Options, General Options. Okay. Go to Maxwell 2D. Okay. And General. Sorry, the boundary assignment. Check these two. Okay. Use wizards for data input when creating new boundaries. Okay, and duplicate boundary and mesh operations with geometry. Okay. Just forgot before I forget this. I will do this with you, demonstrating how to build the project with you, and later I will send a step-by-step instruction of how I did everything to you. Okay, so if you're interested, you can download the student version software and do it yourself. Okay, so but this time I will please just watch. I will demonstrate how to do that. Okay, so this is the first two settings we must check. Okay, and then go to the 3D modeler. Go to 3D modeler in the display rendering. Set the default transparency to 0.8. Okay, this is not compulsory, but when you do this, your model becomes half transparent, and it gives you better visibility of the model. So I always set this by default. Okay. And in the drawing, you please check this one, the automatically cover close polylines. Check this one. Okay. And that's it. Just click OK. And also, in most cases, we'll draw the model with the default unit that is millimeter. So sometimes it is not millimeter, so you need to manually set it to millimeter and click OK. Okay, so that's how we initialize a model setting. Okay, and then after this, we'll start to draw the motor geometry. Let me go back. Okay. So after you create a new model, rename it. Just click here, rename, name it as whole motor. Okay, raw, because this is the first geometry we built. Okay, and actually when I try to model electric machine, I always follow the project manager, okay, step by step, because this is actually what you need to follow to complete the construction of Fe model. The first one is 3D or 2D component. So how to draw the geometry? So the first thing is to draw the geometry. Okay. There are many ways to draw these geometries. Okay. The simplest one is to use the predefined template. For example, if I want to draw the stator, okay, I go to draw, and here, user defined primitive. I'm expert, so this is the useful tools of commercial software I mentioned to you. So I'm expert, okay, and then you go to slot call. Okay, slot call. That is stator call with slot. If you click it, I've already created, this window will pop up. Okay, so this is the geometric parameter window that allows you to set the geometric parameters for this stator geometry. Okay, we'll go through that, each parameter one by one together. Okay, let me zoom in. So this is your stator, outer diameter, your tools, your slot, your tools. Okay, double click it. The first parameter you have is die gap. The descriptions here, that is the core diameter on the gap side. The core diameter on the gap side, then it is this side. Okay, so that's the inner diameter of the stator. Die yoke, which is the core diameter on the yoke side. This is the stator yoke. So this is the outer diameter of the stator. Okay, these are the real value of the Prius machine. Length, for 2D model, you have to set length as 0. Okay, otherwise it won't be a 2D surface. It will be a 3D model, and your 2D solver cannot solve it. Skew. Okay, so this is whether you skew the stator or not. Professor Data also introduced about this. So you can skew the rotor or the stator of a motor to reduce its torque ripple. But the Prius motor does not skew its stator, so we set skew angle to 0. The slot number for slot type, okay, slot number 48, because we want 48 slots. Slot type, so these are 1 to 6 different predefined slot types, but we may not be able to try all of them. I'll show a few to you because the following parameters does not allow you to select all the slot types, but we can try. Okay, so try different ones. So the first slot type 1, is a slot with round end and round tools. Okay, we are using number 2. That's a slot with a round end, but a flat tooth. A flat tooth fit. Okay. 3 and 4 are not available in this case, but we can try 5. 5 is also not 5 is also not available. Okay, let's try 6. Not available. Okay, so that's because these parameters that define for this model does not work for the other type of slots. Okay, it's all right. Number 1 and number 2 are the most common slot types. Okay, so in this case we use the slot type 2. HS0, this is the slot opening height, which is this is the slot opening. So slot opening height is this height. Okay, the height of the tooth fit. This slot opening bridge height. Okay, so sometimes you need to design a stator with closed slot openings, meaning there's no slot opening. Then you set this value to not be 0. Okay, let's say we set 0.2. It will seal up the slot opening and create a 0.2 millimeter bridge. Okay, but that's not the case for the Prius motor, so we set it back to 0. Slot wedge height, the wedge is, I'll show you. this is the slot wedge. Okay, so instead of having a rectangular, a perpendicular angle, it fillet this sharp angle, okay, with the angled line. So that's the height of the Stator 2's wedge. And in this case, it should be 0. So we set it to 0. Apply. The slot body height, also known as the slot depth, is the height of this. Okay, so the height of the slot. Slot opening ways, this is easy. This is the slot opening ways. Okay. The next, slot wedge maximum ways, that is the ways here. Slot body bottom ways, 0 for parallel tooth. Okay, so we want it to be a parallel tooth. Parallel tooth means the two edge of the tooth is parallel. Okay, so it means it has an even ways. So we set this to 0. RS is the slot body bottom fillet, which is the fillet of this slot end circle. Fillet type 0, that is a quarter circle, a tangential connection, or arc bottom. In this case, we use 0. Half slot, we want a full symmetric slot, so we set this to 0. Segment angle, what is this one? Okay, so this is when you try to reduce the computational workload of your computer, you don't use a true round circle. Okay, you use multiple lines. So this is how you set it. Let's see, we set it to 30 degrees. Oh, computer freezing. Sorry, bear with me. Okay, now you can see it used to be a round and smooth half circle. Now it becomes multiple straight lines. Okay, so it's easier for a Maxwell solver to solve geometries like this. Okay, but if you want the true surface or the true circle, you set it to be 0. The length region is again the depth of this model, the maximum depth of this model. This does not affect our model in this case, so we don't worry about that. And here, it's whether you want the real core or the solid core. If you want solid core, it's just a cylinder, and you don't have all the slots. 100 is the region, is a full circle. Okay, whose diameter is the diameter of the stator. So we just use 0. I can show you when we set it to 1, it's like this. Okay, so you don't have a slot, you need to set it to 0. Okay, so this is how we draw the stator, use predefined template. Okay. Rotor, similar, we use draw, we go to draw, user defined primitive. I'm expert. In this case, this is the interior permanent magnet machine. So you select IPM core. When you click IPM core, this window will pop out. Okay. Then you input all the geometric parameters of the rotor. You will get your rotor geometry. Okay. Again, this is the rotor outer diameter, inner diameter, which also the shaft diameter, length 0, because this is a 2D model. We want this to have 8 poles. Okay. The pole type, okay, that sets whether you want flat type, inset type, weight type, or spoke type. In this case, we want to use the weight type, so we set it to 3. When you build your own model, you can try other type of poles. Okay. D1 is the limited diameter of PM ducts. PM duct is the duct, the hole here, the PM slot. Okay. The limited diameter, which is the diameter here. Okay. Meaning this value divided by this value minus this value, divide by 2 will be your bridge waist, okay? The waist of this bridge. The distance between the duct bottom to shaft surface, which is from here, from here to here. This is also the York thickness. The duct thickness, which is this slot thickness, and the rib waist is here. This is the part we call the rib. Rib height 3. Typically 1 and 3 to 5. Okay. So, and this is the minimum distance between the side magnets. So that's the minimum distance between the side magnet. That is, oh, I can't move it. Then the minimum distance between these two magnets, not these two, between these two magnets. And the thickness of magnet, which is this real height or thickness of magnet, that is 6.48. The waist of the magnet, 32, which is the waist of the magnet here. Okay. And you can see the magnet is actually thicker, or you can see it's higher than the magnet slot. Okay. That is because we need this part as a stopper, okay, to secure the magnet at its designated position. Okay, so once you insert the magnet into the slot, it can't move. Okay, if you don't have this stop, it may move up or move down. Okay, so this is how you build the rotor structure. And similarly, you can build the magnet, use the same template. The only difference is here. If you want the core, you set this number to 0. If you want the magnets, you set this number to 1. Okay, so if you set this number to 1, it will create the magnets. Okay. And next part is now we have a stator, rotor, and magnet. The last part is the winding. Okay. The real winding is actually the cross section will be many small circles. Okay. But in a 2D model, it's if we have multiple small circles, that will significantly increase the computational workload of Ansys. So we don't do the real cross-section of copper conductors. We just use one rectangular or other shape of geometry to represent the winding. Okay. In this case, we draw the winding also using the predefined template as lap coil. So when you click lap coil, you will have this. Again, you type all the parameters. Okay, it will create the lap coil of one phase and one pole. Okay, and we need to duplicate these coils. Okay, to create the full circle. Okay. So after you create this one, you create the lap coil, you rename it as phase A, change the color to red, because we normally use red, blue, and yellow to represent phase A, phase B, and phase C. So change its color to red. You click on phase A, and next thing you need to do is to rotate. Okay, you can click here, rotate, or modular. Sorry, I forgot project. I forgot where it is. In the menu. Okay, but the easy way is to select it and just click here. That's rotate. Okay. Okay. Oh, I remember that. It's in edit. So there's two ways to rotate this. Either go to menu, edit, and range, rotate. Okay. Or select it in the quick menu, click rotate. Okay. So you set this to 7.5 degree. We rotate by 7.5 degree. 7.5 degree is the arc angle of one slot. We rotate to here and duplicate, okay? You can duplicate it around the axis by clicking here, set this to 15 degree, total number to 3. This is how you rotate it, okay? So this is done, rotate it. Okay, so remember at the beginning, we only have the winding of one phase, okay? But now by doing this, we have the winding of 3 phase. So you need to change the second one as phase B and third one as phase 3. So this would be your phase B and change its color to blue. Change this to phase 3, change this color to red. Okay, to distinguish these the copper winding of different phase. Okay, then the next thing you need to do is to just hold Control and select all 3 phase windings and duplicate them again, because this is just the windings of one phase. We need the winding to fill every slot. So again, we duplicate around axis. Okay, this time set the angle to 45 and 8. Okay. So now we can get the winding arrangement of all slots. Okay. So it's maybe normally I set phase B to, oh, it's frozen again. Okay, so while it is frozen, you should know the settings of these copper windings is not random. You can see I'm rotating them by 15 degree, 75 degree. It's not a random selected number. That is based on the real winding arrangement, okay? Let's set this to red and this to yellow. Select all of them, duplicate, and finish. Okay, so this is how, oh, why it's all yellow, sorry. Set this to blue. Select all 3 phase, duplicate the round axis to get all windings. Okay, so once we get this, we got the geometry of every essential part. Okay, so we have our stator, the rotor, the magnet, and copper winding. Okay, let me speed up because we also need to do a quiz. So yeah, we started at we started 50 minutes late. So please allow me to have that 15 minutes back. Okay, so when you have this rotor, okay, the whole motor, we can take the advantage of its symmetry. We know both the stator and the rotor are periodical. So we only need to actually model one of the pole, okay? Then the rest part are all the same. So you don't need to model the whole motor. We only need to model one of the pole, okay? So how to do that? Go back. You click in the workspace, press Ctrl+A, select all objectives. Okay, this is blocking me. And you click on split. Select the Y and Z axis. We want to keep the positive side. We want to eliminate, we want to delete the negative side. Okay, so now we only have half motor. Okay, but we only want one pole, right? So again, we select all objective, rotate around rotate around zeta axis. Okay, by minus 45 degree because each pole is 45 degree. If we rotate by minus 45 degree, here we got one of the pole, right? And the rest part are all periodical, they are all same. So again, we select all object, split it, but this time we want to keep the negative side. So now we have the stator and the rotor and magnet and copper winding of only one pole. Okay, next we just rotate it back to X and Y, the quadrant 1. Rotate back by rotating 45 degree. Okay, it's frozen again. Okay, so now we get this. Okay, if we collect all, you can see now we only have 6 windings. We have one magnet, rotor, and stator geometry. But these two magnets are magnets from different pole. Okay, so we need to separate them. Click magnet, go to modular, Boolean, separate bodies. Okay, then we got magnet 1. Let's rename it PM1. And rename the second one as PM2. Okay, and we know magnets has polarities. Okay, because these two magnets are from different pole, so they should have offset polarity. How to set polarity for magnets? So we need to create a coordinate system. Okay, so first you need to change your selection mode to phase. Then you click on the first magnet, and then you click create phase coordinate system. Okay, you can just click on one of the corner, click the second corner. This will create a new phase coordinate, and the x-axis direction will be the polarity of this magnet. Similar, we do the same for the second one. Phase coordinate system. Okay, so this one, the first one, x-axis points inward. This one, x-axis points outward. Okay, and we assign this to coordinate system to PM1 and PM2. Okay, so this is how we assign the coordinate system of the magnet, and also these are our copper winding. Okay, so time's tight. I want to show you the result. So, okay, so I'll go again faster. Okay, so after we set everything, after we set the direction. Okay, let's go to this one. This is the pre-solved model, similar to what we get. Okay, so we only have the geometry of one pole. And this is a copper winding magnet. The direction of the polarity of the magnet are already assigned. The next thing we need to do is to give the rest part a material. So for the windings, we set the material to copper. Okay, so you can find copper in the system library. For the stator and the winding lamination, we set its material. Okay, we select its material from the GFE steel library. You can select the library here. GFE steel is one of the world's largest electrical steel producer. So, the library or the material property provided by GFE is very accurate. So normally I use GFE. In this case, we use this 35 GN 300. Okay, so this is the material for the steel. Okay, it provides the BH curve. the nonlinear BH curve of the material and the loss data, okay? Also for the magnet, we select its magnet material from R0 magnets, okay? In this case, the Prius use N36. We don't have N36 in this library, but we can select N35, okay? So we select N35, 60 degree, select OK. So that's how we assign material to the magnet, okay? And once we do that, all geometric models are all done. The next thing we need to do is to assign the boundaries, the master boundary, the sleeve boundary, and the zero flux boundary, okay? We need to assign the master and the sleeve boundary because this is a periodical model, okay? So we need to tell them how this model repeats itself. So we need to set. How do we do that? Select E, go to selection model, edges. Then you can select this edge, okay? Right click on it, assign boundary, master, and this is correct. So it should be from the center to the outer edge. Select the other, assign boundary, and this time select sleeve, okay? Which one is its master boundary? So you can select master one that is already defined. Relationship, you need to select this one. BS is minus BM, okay? It is because it is periodical, and periodical each period, it's just offset. The magnetic field is offset. So you have to select this one. And by default, when you select this sleeve boundary of this edge, it points from the outer edge to the center. So you need to reverse the direction. Okay, so this is how we set this sleeve boundary. Click OK. I have already set it. So we have already set this one, master and the sleeve boundary. Now we need to set the zero flux. Hold Control, select all the lines here. Right click, assign boundary, click vector potential. Okay, you just need to set this value to 0. That means we want all field, magnetic field, to be 0 when it reaches this line. Okay, so this is what zero potential represents. That's why we call it zero flux. Okay, now if you still remember, I said this is how we need to complete the construction of a model. The geometric models done, the boundaries done, the excitations. Okay, for the first model, we only want to solve the no load model, so we don't need to assign current to the copper windings. But we want to estimate the rotor torque even at no load condition. So you change your selection mode back to object, select the rotor and the magnet. Okay, after selecting them, right click on parameters, assign torque around zeta axis, positive direction, click OK. Okay, so this will help us calculate the torque acting on the rotor at the no load condition. Next is the very important part, which is assigning mesh to each of the component. So first, we select the stator, right click, assign mesh operation on the selection. Here you have two options, on the selection or in the selection. So for a 2D model, which is the surface, you can use on the selection, okay? But when it is a 3D model, which is a solid with a depth, you want to have mesh in the solid part, you need to use inside selection, okay? In this case, we use on selection, length-based. Name it as stator, because this is the mass for the stator. Change the maximum length to 5. By default, it will recommend an element length based on the dimension of your geometry. Okay, it's normally too big. Okay, so in this case, we use 5 millimeter. There's no good way to find the mesh element length. Is just experience. So when you do more simulation, you will know, okay, for a motor with this size, the mesh element size should be approximately this. Okay. Normally, a finer mesh can give you a more accurate result, but the finer mesh also increase your computational workload. Okay, so you can't use an element size that is too small. You can't use an element size that is too big. Okay, in this case, we use 5. We do similar thing for the rotor, maximum length 5. For the magnet, we just select these two geometry, still on selection, maximum length 3, because magnets are smaller. Okay, so that's how we do the mesh. Next is to set the analysis setting. Right click on it, add solution type. Okay, so if you click this, this will pop up. Okay, because FEA is iterative solving process, so you need to set maximum number of passes. So you need to satisfy this. So you need to pass 10 times with error smaller than 0.2 to converge. Okay, and each time if it didn't converge, it refined the mesh by 30%. And this is the nonlinear residue, set it to 0.0001. This is fine enough for our model. Then you are okay. You're ready to solve this model. Okay. Sorry, again, it's frozen. Okay, right click on it, click analyze. It will start to solve the model. This is already solved. Okay, so I can show you a few results of this model. Select the stator, rotor, and magnet geometry. Right click, field. We are very interested in its normally in the no load magnetic static analysis. We are most interested in its flux density. So we plot this field. We plot this field distribution, flux density, magnitude. Click all object, click done. Okay, so this is the field distribution, the flux density distribution in the motor. Okay, so you can see here we have the highest flux density near the bridge. Okay, and also at the slot end. Similar, if you want to, we can also see the flux path. Okay, so select assignment, right click, field, it is a flux line. Flux line of all objects. Okay, so this is the flux line of the motor while there is no load, meaning there's no current. So you can see the flux line just coming from one pole, the magnet from one pole, going through the stator yoke, through the stator tooth, go back to the other pole, through the magnet, through the rotor yoke, and go back to the first magnet. Okay, so this is the flux line when there's no current. Okay, we can also see the flux density in the air gap. Okay, you just need to click the region, reassign. Okay, now this allows to see the air gap flux density. Okay, you can see the air gap flux density is not even. At some part, okay, when it is aligned, where it is aligned with the rotor pole, you have higher flux density. When it is aligned to the rotor Q axis, you have a lower flux density. You can also plot the air gap flux density in XY plot. Go to result, right click, create field report, rectangular. Select the geometry, the air gap, and select B radial. Okay, so actually I created this myself. you by default, you have the magnitude of B, distance along this line, new report. Okay, so this is your flux density in the air gap. We can get the maximum flux density in the air gap at no load condition, approximately 680 Tesla, millitesla. Okay, so this is a very important parameter for machine design because you can do many calculations using the flux density in the air gap. Okay, so I prepared other content, but unfortunately we don't have time to finish them all. So we'll continue this in next tutorial. And in the meantime, I will send the instruction to you, probably to Professor Sakia. And maybe he can help me to distribute the instruction to you if you're interested in doing motor building using Ansys. And again, to do that, you need to download, at least you need to have the student version of this. Okay, and we can try to solve the mesh element limit problem. Now, let's go to the quiz section. Okay, so forget about the end time. I'm sorry for taking extra time. Okay, so you can go to the quiz by using this link or scan the QR code. Yes, no problem. I'll send the link for download Ansys here. Now let's do the quiz. Sorry for taking extra time, and yeah, thanks for listening. If you have any other question, please feel free to ask me. And let me know whether you can access the quiz or not, okay?
Okay, Dr. Clay, thank you so much for your nice presentation. I'll ask the audience if they have any questions regarding today's session. Okay. Okay. Sakia sir.
Hello, is it audible?
Yes, yes, you're audible.
Okay. So let this one finish, the quiz finish. Okay. Whether Dr. Clay, whether they can submit after closing this, after 20 minutes, if we close this one. Dr. Clay. Ansys, is it audible from my side?
Yes, sir. Yes, sir. You're audible.
Okay, okay.
It's okay, but if there's want to stay, like if you want to close the session and the student to submit sometime later, that's also fine. I think it must be it will allow to submit.
Okay, Dr. Clay.
I'm not sure where he is. It looks like he's mute. So maybe
Okay, madam, can you stop here? They can submit after 20 minutes, means within 20 minutes.
Yeah,
Yes.
that's what I'm saying. It's
Okay.
fine. If you want
Dr.
to
Clay,
stop.
you can, they had already noted the link. you please stop sharing this one. We will take one screenshot of the participants.
Sir, I guess, sir, I
Yes,
think his
busy
mic is
somewhere,
off.
I think.
Probably. His mic is off.
Ah,
He might have some problem with the internet. I don't know.
hello, Dr. Clay. Can you stop sharing? I think the participant had noted the link. Okay. So we'll take one screenshot of the participants.
You are mute, Clay.
Yes, sorry. Okay, so when I'm not playing
You
something,
please stop sharing, then we'll take a photograph.
yes.
Participant, please, please open your camera.
Hello, everyone. Thanks for listening this tutorial.
Save it. Okay. ठीक है. This or not? Save, no? Madam, since they will submit in the Google Form, they
Sorry, which one?
they will submit the quiz answer
Yeah.
in the form in the link provided.
Yes.
So can you end up here now?
Yes. We can end up here.
Yes.
That's fine.
Yes,
Yeah,
So
we
all
can.
participants, whether you have noted the link.
The link is also in the chat window, so you can
Okay.
copy from there.
Yep.
Yeah.
So I can extend the answer time. I'll extend it by 1 hour, so you can do the quiz even after this session.
Yeah.
Sorry for taking extra time from you.
No.
Okay, Ansys, you can conclude now. Okay.
Okay. Thank you, Dr. Clay. It was a wonderful session, and thank you, Professor Datta. And I hope the participants found it useful. So we look forward to the next session.
Okay, thank you so much. Thank you for listening.
Thank you.
Thank you for hosting this.
Okay, thank you, madam.
Thank you.
Bye for now. Bye.
Okay, good night, madam.
Good night.
Good night, Clay.
Yeah, good night.
Okay.